Now let's solve a problem using the BS law. When we have a wire carrying current through a straight part pointing this way, and this wire is bended into part of a circle, and then later the current goes away along another straight part. And then we try to figure out the magnetic field created by this current carrying wire at a location here, which is the center of that part of the circle. Then what we can do is we can consider it at three different parts. The first part from A to A prime. In any well, ds cross R is going to be equal to 0 because ds and the R are in the same direction. For the last part, B to B prime, any pieces of small ds that you consider is going to be in the direction 180 degrees away from R. ds this way, R this way. And the sign 180 equal to 0, ds cross R is equal to 0 when they are in the opposite direction. So what only matters is this part from A prime to B. And in this circle part, we can consider it to be many tiny pieces of ds. And again, each of that is going to create a small amount of a B field at this location. And the ds cross R, it's important to notice because this is a perfect part of a circle. We have the ds in the tangent direction, and R pointing to the center of the circle is in the radius direction. So the angle between them is 90 degrees. They are perpendicular to each other. Also notice that the R is the vector going from the source element pointing toward the observation point. It is not going from the center outward. Okay? So dB cross R for this part is going to be equal to, ds cross R is going to be equal to the length of ds, a small segment, multiply 1, multiply sine 90, which is 1, and then ds cross R gives you a vector which is into the page. 4 fingers along ds, bend toward R, you have something into the page. That is your dB. Okay, so, and then you have your into the page. You can define into the page to be negative k direction. Or if you like, you can define to be positive k direction. Just to be clear that into the page, it's negative k. And here, out of page is k. Okay? Having this in mind, we can start using the BS law. Okay, so again, dB is equal to mu 0 I over 4 pi R square ds cross R. And that has a particular value of mu 0 I over 4 pi R square. R is the distance from ds to the observation point O. Here, R is equal to A, which is the radius of this part of the circle. So you have A square. Here, we have ds cross R essentially equals to ds itself. And that's in the negative k direction. Okay, that's this vector. Let's check another one. If we take a piece of ds here and cross product with the unit vector pointing to the center observation point O, again they are perpendicular to each other, 4 fingers along ds, bend toward R, the result is again into the page. So you find out this is a simple problem. Every piece of ds along this circle cross R is going to give you a result into the page. When they are in the same direction, they can be integrated together. So we know that the total B field equals to the integration of the dB, which is in the direction of negative k. You can take it out. That's the direction. All of them share the same direction, and we are integrating something numerical without direction, that. Okay? And then where are we going? We are integrating from the A prime point to B point. We are taking tiny pieces of ds all over the place that goes from A prime to B. Again, whatever is a constant, you can take out from the integration. You have negative k, which is only represented into the page direction, mu 0 I over 4 pi a squared. And then integrating from A to B, A prime to B ds. You're going to find your answer. What is the integration of ds going from A prime to B? You may say, oh, that is equal to the total arc length of this part. So if you have part of a circle like that, that's part of a circle, and that's total length equal to s. And how to calculate that? If you see the center of the circle, which is here, and this is the angle theta. We should know that this s, and this is a radius r, okay? And we should know that this s is equal to r multiply theta when you have the theta in the radius unit. In another word, if you are talking about integrating ds for a full circle, you are corresponding to an angle of 2 pi with radius r, then you are getting 2 pi r. When you are not integrating a full circle corresponding to the particular angle that you are facing in radius, the arc length should be equal to r multiply that angle. If this is 60 degree, the s is not 60 multiply r. It's going to be 60 degree corresponding to a quarter, 1/3 pi multiply r. Okay, then plug that in, you solved the problem.